Hi, I'm Yang, and I'm going to be presenting on faster Maxflow via improved dynamic spectral vertex sparsifiers. This is joint work with Jan van den Brand, Yu Gao, Arun, Jambulapati, Yintat Lee, Richard Peng, and Arun Sidford. To start, I wanted to introduce the maximum flow problem that we study. In the maximum flow problem, we have a directed graph G with a source S, sink T, and capacities UE at least 0. The graph has M edges and vertices and some maximum capacity U, which throughout the talk, we can think of as some number which is polynomially bounded. Think U is like M squared or M cubed or something like that. In the picture, we have an example graph with a source S and a sink T, directed edges, and the capacities are listed. The goal of the maximum flow problem is to route a flow on the graph, where a flow we can think of formally as an assignment of a real number to the edges of the graph. This flow needs to satisfy several properties. The first property is the demand constraint, which says that at all vertices other than S and T, the amount of incoming and outgoing flow must match exactly. Our goal is to maximize the amount of total flow which leaves S, equivalently the total amount of flow that enters T. The capacity constraint is that the amount of flow on every edge must be at least 0, and at most, its maximum capacity UE. So the problem would be to route a flow between S and T, satisfying the capacity constraints, demand constraints, while maximizing the total flow. Our results are that we can solve the max flow problem and min cost flow in time m to the 3/2 minus 1/58 up to logarithmic factors. This improves over previous results for maximum flow and min cost flow for sparse graphs with arbitrary polynomial capacities U. Also, in sparse graphs, it improves over m plus n to the 1.5, which was achieved for min cost flow earlier. I wanted to mention that recently, an algorithm was given to solve max flow and min cost flow in almost linear time for polynomially bounded capacities after this. To understand the context of this work, it's useful to make the following definitions. First, it's known that we can solve maximum flow in square root m iterations of approximate electrical flows, which is a other type of flow problem. An electrical flow asks to route a flow, routing demand D, that minimizes the energy of the flow, which is the quadratic energy, the sum of resistance times the square of the amount of flow on the edge. To compute an electrical flow, it corresponds to solving a linear system in the graph, precisely inverting a Laplacian matrix. Therefore, you can compute electrical flow to high accuracy in almost nearly linear time due to a seminal work of Spielman and Ten. So directly implementing this method of computing it exactly and going for root m iterations requires time m to the 1.5, because that's root m iterations and m time. So that's m to the 1.5. As you remembered, our result is a little bit better than m to the 1.5. And to achieve this, we leverage the important property that the electrical flows only need to be approximate, and in a very crude sense even. Essentially, we only need to be able to detect edges that have a high contribution to the electrical energy. In other words, edges where RE FE squared occupies a large fraction of the energy of. I'll formalize this in a bit. So in light of the previous discussion on approximate electrical flow sufficing for max flow, we try to find an electrical flow actually in sublinear time using the following data structure set. Given a graph G, where each edge has resistance RE, we want to build a data structure that has the following properties. It supports an initialize operation, which you can initialize through fg, with the desired accuracy parameter epsilon. Additionally, it supports edge updates, where the resistance of edge E gets changed. And it supports an operation which we call locate, which is the critical operation necessary for the algorithm. Let F be the current electrical flow, which we don't know because we're not writing the whole thing down explicitly. The algorithm wants to, in sublinear time, return a set S containing all edges that have at least epsilon squared fraction of the total energy. In other words, RE FE squared is at least epsilon squared times the energy of F. Additionally, for each edge E in this set S that we return, we wish to estimate the square root of its energy up to an additive epsilon. And yeah, that's the data structure problem. Our goal is to achieve an amortized runtime of m to the 1 minus delta for some positive delta, and then epsilon to the minus O of 1. And it would be important that this data structure works against adaptive adversaries in some sense. So an adaptive adversary is an adversary which makes future queries depending on previous responses. This is important in general to apply data structures to algorithmic problems, because the responses of the data structure influence how the algorithm progresses and therefore influences future queries. So we need some data structure for this problem that works against adaptive adversaries. This was achieved in a weaker sense by previous works. And by weaker, I mean it doesn't exactly solve this. It solves a relaxed version, which is enough for Maxflow. And it doesn't completely work against adaptive adversaries. It works in a looser sense that leverages properties of the maximum flow problem to work. But we'll try to focus on achieving amortized runtime m to the 1 minus delta over poly epsilon versus adaptive adversaries, which we do achieve. As for why this gives a faster Maxwell algorithm, intuitively, it's because we have amortized runtime m to the 1 minus delta for square root m rounds of the outer loop, and that's m to the 3 halves minus delta. Formalizing this requires a bit of work, but it was kind of done previously, and it's doable. So yeah, towards this data structure problem, our main contribution is to give several simplifications and improvements to the previous algorithms for solving this dynamic electrical data structure and other dynamic electrical flow data structures. Our contributions involve several broad improvements to previous works. And they're not even immediately related to Maxflow, so I would recommend that when thinking about these problems, we can just think of them in a self-contained way without really referencing maximum flow or even electrical flows in some sense. So yeah, here's the improvements that I wanted to touch on. The first improvement is that we give a faster algorithm for sampling random walks in graphs in the following sense. Given a graph G and a vertex V, we wish to sample a random walk from V that hits L distinct vertices. It's important that the vertices are distinct, starting from a fixed vertex V. And we wish to approximate the total length of the random walk up to a 1 plus epsilon factor. We'll clarify the setup when we get to it. Our algorithm surprisingly uses a Morris counter to an approximate counting algorithm to efficiently do this. Another piece is that for the previous data structure problem, previous works used ideas from computing a dynamic Schur complement, which is a graphical structure, to solve this problem of locating high energy edges. We basically showed that dynamic Schur complement is in fact just enough to study and more or less give a black box reduction. Finally, I said it was important that our algorithm works against adaptive adversaries. However, the most natural data structures all work against oblivious adversaries because they are very randomized. However, we show that in the context of this problem and in general vector estimation problems, that adaptive and oblivious are very similar, and I will explain how that works. So for the remainder of the talk, I was going to first touch on the reducing adaptive to oblivious a little bit. And then I was going to focus on describing the random walk sampling algorithm, which is very nice. Now let me explain what I mean by reducing adaptive to oblivious for vector estimation problems. And we can think of this kind of independent from even electrical flows or Maxflows. So here's the problem that we studied. There's a hidden sequence of vectors, v1 to vt in m dimensions, that's given adaptively. These vectors, they're hidden, but we have access to the coordinates in some ways. Each vector is L2 normmost 1, and we are given oblivious data structures that given v return a w, which is probably going to be sparse in fact, with w minus v L2 norm and most epsilon. It's important that you can check basically that you can return a w that's close in L2 kind of in a randomized way with L2 norm most epsilon. So let's say we have data structures d epsilon over 2, d epsilon over 4 that solve this problem obliviously. And the amortized runtimes are t epsilon over 2, all the way to t epsilon over 2 to the k, which increase. Intuitively, this just means that when I want a higher accuracy data structure, a data structure with accuracy epsilon over 4 instead of epsilon over 2, the runtime should be increasing, which And our goal then would be, given these oblivious data structures, to give a adaptive data structure that can estimate each vi with an L infinity error, because that's the goal of our dynamic electrical flow data structure. We wish to detect the large coordinates of v essentially, which is an L infinity problem. So given this, we showed that you can build an adaptive data structure that returns wi with an L infinity difference from vi that's almost O tilde epsilon. And the expected runtime is the following formula. It's O tilde t epsilon plus a half t epsilon over 2 plus a fourth t epsilon over 4 plus etc. plus 1 over 2 to the k t epsilon over 2 to the k, and then plus 1 over 2 to the k times m. Okay, so let's understand why this theorem is true, or intuitively why it's true. The reason intuitively why it's true is because every iteration, we want to get error epsilon. So what we do is we first make a call to d epsilon, the data structure that will return something with error epsilon, L2 norm error epsilon. We call it once, and about half the time, that will be enough information for us to output some wi, which is good enough, adaptively even. But half the time, we're going to have to ask for higher accuracy, where we're like on the boundary of what to decide. And then half the time, we'll have to go to the next error because we're still like on the boundary. And we go for k layers like this. After k layers, well, the runtime is getting so expensive that we just give up and we just output m exactly. Like we just read off v, which is an n-dimensional vector, and just kind of output the whole thing. So that's intuitively what's happening. A little more precisely, the way we ensure adaptivity is that the output wi we shoot for is vi plus O tilde epsilon times a normal distribution. In other words, the wi is going to be vi plus O epsilon times some Gaussian noise. To output a wi from this distribution, we're going to first call d epsilon to return a vector w, which is L2 close to v. And with about probability 1/2, we're going to output w plus z, where d is some conditional on the normal distribution. Otherwise, we're going to output d epsilon over 2 to return some new vector w, which is closer now, and then we'll output w plus z, where z is some new conditional with probability 1/2, etc. You can keep repeating this, and then after k phases, we'll give up and read vi completely. As for why this works, the idea is that because we're adding a lot of noise, epsilon noise, we can kind of sum up all these conditional distributions, and the total mass when you add them all up is going to end up being the final distribution. And you can just kind of carefully make sure that that's what's happening. And yeah, that's all I'm going to say about this, but that is the idea. you try to simulate, well, you output VI plus Gaussian noise, and you simulate this by calling the oblivious data structures and using them to make decisions. You just kind of simulate the file distribution. Okay. So yeah, now I'm going to shift gears and talk about the other aspect of our improvements, which is sampling random walks and estimating their lengths. The input for this setting is an undervector graph G, where each edge is assigned both a weight and a length. Let's assume for simplicity that the graph G is sparse and is Maxwell degree O of 1. Given a vertex V, we want to sample a random walk from V that hits L distinct vertices, and we want the algorithm to also return a 1 plus epsilon approximation of the length of the random walk, where the length is given by LE. Such random walks are very related to electrical flows, and in fact form the basis for dynamic electrical flow data structures, as in previous work. To clarify, the exit probabilities of the random walk are proportional to these weights, which is where the weights come in. In other words, for any neighbor U of V with edge E, the probability that V will go to U is given by WE divided by the sum of all the neighboring edges to V of their weights. We're exiting a vertex proportional to the weights. The reason that this setting is non-trivial is because you can't just naively simulate the walk, because the weights could potentially be large. For example, let's consider the following picture. If you start at the first vertex and you want to random walk until we get to the last vertex, notice that we'll get stuck on the middle edge for a lot of time. And the reason we'll get stuck is because the weight is 100, so we'll just be using it a lot, over and over and over. Yeah, so you're going to keep using the middle edge and you kind of can't escape it. However, we need to somehow still be able to estimate the length of the walk, even if you just keep going back and forth, and to simulate what's going on. So let me explain how that's possible. So just to build some intuition, I'm going to explain some previous observations in previous work. So first, let us ignore estimating the length of the walk. And let's just focus on how do we find a walk to hit L distinct vertices, and what are the vertices? I claim we can do this in time L squared, basically. The idea is that if the current set of vertices is S, we can just compute a new vertex, like the next distinct vertex we hit by solving a Laplacian on the induced subgraph G restricted to the set S. This is O of L edges because we're assuming it's an induced subgraph. So we're assuming that G has maximum degree O of 1. So it has O of L edges. So you can solve the Laplacian in O tilde L time for a total runtime of L squared. So that's the algorithm for if you just wanted to get all the vertices. However, the previous algorithm that also estimated the lengths, in addition to finding the vertices, took much larger runtime. It took time L to the omega plus 1 plus epsilon to the minus 2 by using matrix powering. So here omega is the matrix multiplication exponent. What we show is that you can improve this runtime to L squared epsilon to the minus 2, which almost matches the time to sample the vertices visited in the walk, basically. Remember, the time to sample the vertices was L squared. In an extra epsilon to the minus 2 time, we can also estimate the length after 1 plus epsilon. To explain how this is possible, I wanted to introduce Morris counters. So a Morris counter is an algorithm which stores an integer x, which is at most n, which undergoes increments over time. And we only want to store it up to a 1 plus epsilon factor. The catch is that the algorithm is only ever allowed to be in O of epsilon to the minus 2 distinct states. Whereas state is just like, you should think of like number of memory states that the algorithm could possibly be in. Naively, the number of states is n because I just stored the number I'm at. Store if I'm at 1, 2, all the way up to n, and that's n states. Epsilon to the minus 2 is much less. So the Morris counter achieves this epsilon to the minus 2 states. The Morris counter and its analysis by Nelson and Yu. So the idea is that the state is always just going to be a number of the form 1 plus delta to the I, based so that you hit every possible, 1 plus epsilon interval, except it was a little smaller. It's epsilon squared over poly log n. When x, this integer we're trying to store, increments, and our current state is 1 plus delta to the I, we're going to move up to the next state with probability 1 over 1 plus delta to the I plus 1 minus 1 plus delta to the I. This is so that the location, well, that we're at is unbiased. We're adding 1, so we're going to increase the next state with probability so that our expected increase is exactly equal to 1. Interestingly, you can show that this algorithm will maintain a 1 plus epsilon approximation with high probability. And I'm not going to explain the proof, but it's very interesting, and I invite everyone to go check it out. But yeah, that's the algorithm. You just kind of maintain an unbiased estimator at these powers of 1 plus delta. To see how it's applicable in our algorithm, remember that the problem we wanted to solve is to sample a random walk from V that hits L total vertices and returns a 1 plus epsilon approximation of its total length under L. So to do this, we're going to create an augmented graph G prime with a new vertex set V prime and edge set E prime. Every vertex in this augmented graph V prime is going to consist of a pair VI, representing that the random walk is currently at the vertex V and the Morris counter is at 1 plus delta to the I. For an edge Vi out of V to vertex U in the original graph out of Vi and V prime, we're going to construct a set of vertices that it goes to. If the length is LE, then we're going to send Vi to Uj, where J is the result of simulating the random walk, simulating the Morris counter, incrementing LE times. So we're going to simulate adding LE Morris counter steps, and that's how we're going to send Vi to Uj. Notice that the number of vertices and edges has increased by a 1 over delta factor, an epsilon to the -2 factor, because the I can be at most O tilde 1 over delta things, because the Morris counter is powers of 1 plus delta. Intuitively, this will increase the runtime by an epsilon to the -2 factor multiplicatively. So our runtime was originally L squared, so now it's L squared over epsilon squared as desired. There's a few technical details that I've glossed over, but this is the basic idea. And yeah, that's how you use a Morris counter to sample a random walk and estimate its length up to a 1 plus epsilon factor efficiently. To conclude, we gave a min cost flow algorithm that ran in time m to the 3/2 minus 1 over 58 polylog m. We introduced several broad techniques that are not even directly related to maximum flow, but could just be applicable to many settings. We show that you can simulate random walks and estimate their length critically using Morris counters. We can reduce adaptive to oblivious adversaries for the problem of returning approximate vectors. And we also show that dynamic electrical flows can be directly reduced to dynamic Schur complements in a fairly black box manner. As for open problems that are still left, I actually think that it might be possible to sample the first L vertices, distinct vertices for a random walk string at V in O of L time without the L squared, which would be very interesting. Using our Morris counter algorithm, this would probably also get an approximate length in time L epsilon to the -2. The reason why I think this might be possible is because the algorithm of Schild solves the case L equals M with a fairly complex algorithm, where the goal there was to sample a random spanning tree. So I'm wondering if using ideas from that can allow us to sample a random walk starting at V that hits L distinct vertices in time proportional to O of L. Additionally, it would be interesting, even independent of applications to maximum flow, to design faster algorithms for dynamic electrical flows, and either against oblivious or adaptive adversaries. Both would be interesting. If the data structure is sufficiently strong, it might lead to a min cost flow algorithm that runs in time O tilde M, and the parallel depth is square root M or square root N, which is not known. And yeah, that's my talk, and that's the archive link for the paper.